few more numericals related to the transmission lines and its parameter. So last class few examples we have solved which are very easy and hit and trial method. By substituting the values we can determine the outputs. Similarly, today we are going to discuss a few more numericals which will little bit complex, little bit need to be understand, and then we can proceed it. Okay. So here I have given one question. Let me discuss first. The characteristics of a lossless line is given as Z0 50 ohm. That means characteristics impedance is 50 ohm. And propagation constant is gamma, that is 0 j.2 pi. So that is nothing but beta value is 0.2 pi rad per meter. Okay. Since it is a lossless line, my alpha term is 0. Okay. Alpha term is 0 and it is operating at a frequency of 60 megahertz. 60 into 10 to the power 6 hertz. And we have to calculate what is L and what is C for the line. It is easy one. So first of all, with the help of Z0, you can write root over of LC. Okay. And beta we know omega root over of LC. Okay. Now if you multiply this Z0 and beta, you will get some relation in terms of L or in terms of C. Similarly, if you divide these two, you will get one more sort of solution. So if I am going to divide beta divided by Z0, you will get omega into C, from which capacitance can be identified as beta omega into Z0. So beta is how much? 0.2 into pi. Omega is how much? It is 2 pi f. And Z0 is how much? Z0 is 50. If you solve this, you will get the capacitance value, which is near about 33.3 picofarad per meter. Picofarad per meter. So this is my answer. Similarly, if you multiply these two, you will get around L C Z0 square, or from this relation also you can determine by taking square it. L is equals to C into Z0 square. So it is 33.3 into 10 to the power minus 12, and Z0 square is 50 whole square. So if you solve this, your inductive value will become around 83.3 nanohenry per meter. So this is your L and this is your C. So first part is over. Next, as it is given, a load impedance ZL is there. Okay, a load impedance ZL is located at Z is equals to 0. What is the shortest distance from the load point at which the input impedance R plus J0? That means we have to identify that particular position at which your input impedance will have only the real component and the imaginary component is 0. So how to proceed this one? The simple technique is, first of all we have to identify the input impedance relation for the lossless line. Once the input impedance relation is identified, then one common factor is called, that is 10 beta L. Beta L is nothing but electrical displacement, and that L will identify the shortest distance of the presence of the load at Z is equals to 0. So let's see how to proceed. So step by step we will see. Let me erase this. So as we know, input impedance for lossless line is Z0 ZL plus JZ0 10 beta L divided by Z0 plus JZL 10 beta L. Okay. So this is the input impedance relation for lossless line. Now whatever the data is given, you substitute each and every one. So for example, here Z0 and this is ZL by Z0 plus J10 beta L divided by 1 plus J ZL divided by Z0 10 beta L. Okay. So just I have took Z0 common from the numerator and denominator. So ZL by Z0. So ZL is 60 plus J80 divided by Z0 is 50. So it is 1.2 plus J, how much it will be? 1.6 around. Okay. So it is 1.6. Substitute this value. And here let us consider this beta L as X, or you can write this is 10 beta L as X. Let us consider this one because this X we have to determine. Now 50 whole into, it is 1.2 plus J 1.6 plus Jx. Okay. Denominator 1 plus J 1.2 plus J 1.6 whole into X. Okay. Now you need to separate which one is the real part and which one is the imaginary part. So Zin is equals to 50. In numerator we can write 1 plus 1.2 of J of 1.6 plus X whole divided by 1 minus 1.6x, then plus J 1.2x. Okay. So this is the relation we will get, because this J when you will multiply, it is 1.2J into X, one component. Another is J into J is minus 1. So it is 1 minus 1.6 into X. So this is my input impedance. Okay. Now as it is the hint is given, input impedance is the real part is existing but the imaginary part is 0. That means you have to solve this one as real part and imaginary part. How can we solve? With the help of componendo and dividendo method. So it is 1 minus 1.6 minus J 1.2x whole divided by 1 minus 1.6x minus J 1.2x. Now multiply this whole term and multiply with this 50, you will get around, and which is equals to Rn plus J0. So that means when you will solve this complex term, you will get one real part and your imaginary part. Only the simple thing is that only the imaginary component you have to make it 0 in order to determine this shortest distance. Okay. So after solving this, your equation you will get for the imaginary term, for imaginary term is 1.2 whole square x minus 1.6 plus x whole into 1.6 1 minus 1.6 into x is equals to 0, or 1.6 x square plus 3x minus 1.6 equals to 0. So this is the equation you will get after the imaginary part you have to determine. You have to make that imaginary part as 0. So I have made the imaginary part as 0, and you have to form a quadratic equation. So once this quadratic equation is known, you have to determine the roots of this x. Since it is a second order quadratic equation, means x square, that means there are two roots will be there. If you solve it, your roots will become, one is 0.433 and one is minus 2.31. So these are the two roots of x. After solving the quadratic equation, you will get two values, x is equals to 0.433 and minus 231, and the distance, electrical displacement, won't be a negative quantity. So what I will do, I will take x is equals to 0.33, that is 10 beta L is equals to 0.433. So what will be my beta L? It is 10 inverse of 0.433. So tan inverse of 0.433 near about 0.409 you will get. Okay. Now beta value is how much? Beta value is 0.2 pi. Okay. And what will be our length? So length I can determine L is equals to 0.409 divided by beta. So it is 0.409 divided by 0.2 pi. So my length will be 0.65 meter. Okay. And when, or you can write it is 65 centimeter. Done. So like this you have to answer your question, because here indirectly is given that input impedance will have a positive term and real part, and imaginary term is 0. So that means you have to calculate the input impedance, substitute the value, calculate this 10 beta L, take this beta L as a component, and L is we have to identify. So this is the simple process through which we can identify the length, at which the input impedance is having a real part, imaginary part is 0. So that is the hint is given, because this input impedance, after solving this, will get a complex term, real part and imaginary part. So how to identify? Make that imaginary part as 0 and you will get these sort of relations. Identify the roots, make the equation as in beta L terms, and your L will be our 65 centimeter. So this is the one sort of question which is a little bit, I think it is a little bit tricky question, through which we can identify the input impedance also, as well as at which particular position that input impedance is placed, so that it will have a real value only. Okay. So this is one sort of question. One more question we will take. Okay. So this is one more question. So here we have to prove the transmission coefficient. Here it is written so that our transmission coefficient is defined as tau suffix L is equals to VL divided by the incident potential, which is equals to 1 plus reflection coefficient at the load, which is equals to 2 ZL divided by ZL plus Z0. And we have to determine the transmission coefficient for the different set of lines. First, if the load is terminated with impedance n times of Z0, what will happen to our transmission coefficient? Similarly, the short circuited line, then open circuit line and match line. So these are the conditions are given. So it is quite easy. So first of all, we need to prove it, this one. So as it is given tau L transmission coefficient, that is VL divided by V0 plus. Okay. Now what is VL? VL is nothing but it is load current into load potential, load impedance ZL. So it is IL into ZL. And what is this V0 plus? V0 plus is half of V0 okay, plus this you can write at the load term Z0 and IL, half of VL plus Z0 into IL. Now if you take these two upper side, you will get 2IL into ZL, and here you will get in denominator VL, Z0 and IL. Now what you have to do, you have to take this IL common from the denominator. If you are taking common from the denominator, this numerator IL will be cancelled out. So I will get 2ZL VL by IL, that is nothing but ZL, and this is Z0. So it is proved, transmission coefficient. One more method, transmission coefficient is 1 plus reflection coefficient at the load. So 1 plus reflection coefficient at the load, we have ZL minus Z0 divided by ZL plus Z0. You have to take this numerator part, so you will get 2ZL divided by ZL plus Z0. So both are same or not? Yes, both are same. So that means this is the first proof. Okay. So this is called as our transmission coefficient. Next, we have to find the transmission coefficient if the load impedance is n times of Z0. So for first case, for load impedance n times of Z0, then the transmission coefficient twice n into Z0 whole divided by, in place of ZL substitute n Z0 plus Z0. Okay, take this Z0 common, you will get twice n divided by n plus 1. So this is your transmission coefficient. Okay, then second, for short circuited line, ZL is equals to 0. Now your transmission coefficient is directly proportional to ZL. So if ZL is 0, transmission coefficient is also become 0. Okay. Then for open circuit line, ZL is equals to infinite, then our transmission coefficient we have to see how to calculate. So we have 2ZL divided by ZL plus Z0. Okay. Now what you have to do, you have to take this ZL common from the denominator. So if you are taking common, you will get this sort of relation. So this is ZL 1 plus Z0 by ZL. Okay, this ZL will be cancelled out, twice divided by 1 plus Z0 divided by ZL. And we know that something by infinity is 0, so this whole component is tends to 0. So we will get 2 divided by 1, that is 2. So transmission coefficient for the open circuit line will be 2, because the reflection coefficient is 1 for the open circuit line. So transmission coefficient is 1 plus reflection coefficient, so it is 2. Okay. Similarly, match line for ZL is equals to Z0. Now tau L is equals to 2ZL divided by ZL. This is the general equation. You need to substitute ZL is equals to Z0. So this is numerator is ZL, this is ZL plus ZL. So here you will get 2ZL. So transmission coefficient is 1. Why? Because the reflection coefficient for the match line is 0. So 1 plus 0 is 1. So this will be 1 for the match line, 2 for the open circuit line. This is open circuit line. This is match line, and 0 for the short circuited line, and this is the given impedance. Okay, so this is the basic relation. Done. So like this question may come in your exam. It is a tricky questions, okay, but you need to identify these relations. One more question we will take. Okay. So this is one more question. So as I have written, a lossless line with a characteristics impedance of 60 ohm is connected to a source Vg is equals to 10 angle 0 volt and Zg is 50 minus J 40 ohm terminated with load impedance J40. Okay, let me draw the figure first. So these are the two wire line where load is connected. Okay, ZL is equals to J40. Now this is the two wire line. Here the Zg is present. Here the Vg is present. Okay, and the length is L for it. This is the two wire line. Okay, so this is A, it is A bar, it is B, it is B bar. Z is equals to 0, Z is equals to L. L is not given, for that I have written as a L. Now if the line length is 100 is given, let L is equals to 100 meter. Okay, beta is equals to 0.25 rad per meter. You have to calculate input impedance and the potential. Okay, input impedance and potential at the sending end. Sending end means at this point. Here Zin we have to calculate and the plus minus B. Okay, so these are the two factor you have to calculate for the first time at Z is equals to 0 first. Sending end means Z is equals to 0. Next, at the receiving end. At the receiving end means at distance Z is equals to L means that is 100 or depend upon this length. Here you have to find out what is your input impedance. Let us consider this is Zin dash and that is V. Okay. So let us consider like this. So this is the second case. This is the first case. This is the second case. Next, 4 meter from the load. 4 meter from the load means from this 4 meter. So that means from this it is 4 meter. Left is how much? Left is 96 meter. So at this point you have to find the input impedance and potential. Then 3 meter from the source. 3 meter from the source means here, near about at this particular, from here, from Z equals to 0 to this is 3 meter and rest is 97 meter. So like this you have to identify the points, identify the input impedance and identify the potential. So one by one we will see. So let us consider first part. A, sending end. Okay, sending end means at Z is equals to 0. So load is present at a distance of L. So how to calculate? First I will calculate beta L. So beta L, beta is equals to 0.25 and the length is how much? Length of the line is 100. So it is near about 25 we will get. Okay, 25 radian, or it is in angle, it is 352.4 degree. Okay, 25 into 180 divided by pi, you will get 352.4 degree. So this is my beta L. Next, input impedance, simple relation, lossless line means I will write ZL plus JZ0 10 beta L divided by Z0 plus JZL 10 beta L. So all the values are given. So it is 60. ZL is how much? Load is J40. Okay. J Z0 60. 10 beta L is 352.4 degree divided by 60. Then this ZL is J, so it will become as a minus 40 10 of 352.4 degree. So if you solve this, your input impedance you are going to get is around J 29.357 ohm. So this is the input impedance you will get. Okay. So this is the input impedance. Now we have to calculate the potential. So potential at Z is equals to 0 is nothing but V0. Okay. Now how to calculate V0? We have a small figure that we have drawn in the last class. So this is Vg, this is Zg, this is Zin, and here it is V0. Okay. So with the help of this figure you can determine V0. So V0 is equals to how much? Potential drop across Zin, and here the current is I0. So it is I0 into Zin. So I will write Zin divided by Zin plus Zg into Vg. So this is my potential. Done. So what is Zin? Zin is J 29.375 whole divided by J 29.375, and Zg is how much? Zg is 50 minus J40, and what is Vg? Vg is 10. Simple. Solve it. It is a complex term. So when you will solve this V0, you will get around 0.575 angle 102 degree volts. So potential V0 is 0.575 angle 102 volt. So this is my potential, this is my input impedance. This is with respect to the sending end. Now we will see how to determine at the receiving end. Okay, let's see. Let me erase it. Since the board is small, so I have to erase all these things. So next is at receiving end. Now at receiving end you can see that Zin is equals to ZL, because at this particular length at 100 meter input impedance is same as your load impedance. So here I will write ZL is equals to Zin is nothing but J40 ohm. Simple. Because there is no further distance, it is the end point. So at the end point, if you are measuring the input impedance, it is same as the load impedance. Okay. Next, we have to calculate the VL. So VL means potential at Z is equals to L. So V at Z is equals to L is VL, and for this we can write the relations. As we know, V0 is equals to VL e to the power j beta L. Since it is a lossless line, alpha term is 0. So in place of gamma, I am directly writing beta L. So here VL is equals to V0 e to the power minus j beta L. So this V0 already we have determined how much in the previous one. V naught is equals to 0.575 angle 102 degree volt. So same potential I am using. So here it is 0.75 angle 102 degree e to the power j. Beta value is how much? 0.25. It is 0.25. And what is its length? Length is beta L term already we have determined, that is 352.4 degree. Only you need to solve it. If you solve this, you will get 0.575 angle minus 250 point angle volt. So this is the potential and this is the impedance. At which point? At the receiving point. Simple it is. No need to calculate Zin. Zin is only calculated for a certain distance from the source end. So at the sending end, if it is taken, the trick is you have to take the total length. If the receiving end you have to take, that means at this point input impedance is same as load impedance, and with the help of this relation, which is the solution of the wave equation, that is VL is equals to V naught plus e to the power minus j beta L. Substitute this V naught value, e to the power minus j beta L. Beta L already we have calculated, that is 352.4 degree, and VL is equals to this much. So this is about at the receiving end. Next we will calculate 4 meter from the load. So 4 meter from the load means from this side, and 3 meter from the source means from this side. Okay. So step by step we will see. So 4 meter from the load. Okay. So from the load means your length is equals to 4, because at this point we are calculating now. At this point, because 4 meter is this. Okay. So at this point input impedance and potential we have to calculate. So at L is equals to 4, so beta L, beta is 1 by 4 into 4 is 1 radian per, only radian, because radian per meter is this. So its value is 57.3 degree. So beta L is equals to this much. Next, you have to calculate Zin. We have a relation Z naught ZL plus JZ naught 10 beta L divided by Z naught plus JZL 10 beta L. Okay, all values are known. Substitute it. So it is 60. ZL is J40 plus J60 1057.3 degree divided by 60 minus 40 1057.3 degree. Okay, if you solve this, near about J3487.1 ohm. So this is your input impedance. Okay. Once this input impedance is known, next you have to determine what is the potential. So potential is VL e to the power j beta L. Okay. VL already we have determined. Directly we will substitute what is the VL value. It is 0.575 angle minus 250.4 degree whole into e to the power beta L is how much? 57.3 degree. So you will get 575 angle minus 193.1 volt. Okay, so this is the potential at distance L is equals to 4. So it is 0.575 angle minus 193.1 degree. This much volts. Done. This is the input impedance. This is the potential at a distance L is equals to 4 meter from the load. Okay. Next, similarly, we have to calculate 3 meter from the source. So the formula will be same. Let me erase once again and will write. Next, D 3 meter from the source. So if it is 3 meter from the source, that means how much meter from the load? It is 97 meter from the load. Because it is 3 meter from the source means the rest of the distance is 97. So our length will be 97 meter. So beta L is equals to, beta is 1 by 4 and length is 97. Why 97? Because now we are at 3 meter from the source. 3 meter from the source means at this particular point. And how much distance is left? The total left is 97. So that 97 I am going to insert it, because last time we have seen 4 meter from the load, so length we have considered 4. Why always from load? Because input impedance is depend upon the load distance. Okay, so beta L is equals to this much. Now if you solve this, you will get around 309.42 degree. So this is my beta L. Now what is input impedance? Same relation, ZL J Z0 10 beta L divided by Z0 plus J ZL 10 beta L. If you substitute all these values, now what is Z0? Z0 is our 60. What is ZL? ZL is J40 10 309.42 degree divided by 60 minus 40 10 of 309.42 degree. So now if you solve this, your input impedance you are going to get minus J 18.2 ohm. So this is your input impedance, minus J 18.2 ohm. Okay, so this is your input impedance. Similarly, next we have to calculate the potential for a distance of 97. So as we have calculated distance at the sending end for 100 meters, similarly only in place of 100 meters we have to substitute 97 meters. That's it. So V is equals to VL e to the power j beta L. Okay. So VL already we have determined 0.575 minus 250.4 degree e to the power j beta L is 309.42 degree. So if you solve this, you will get 0.575 angle 59.2 degree volt. Always mention the units. If you do not mention the units, the marks they will deduct. Okay. So input impedance and potential. 3 meter from the source, that means length of the line will become now as 97 meter. So for the 97 meter we are calculating input impedance and potential. Okay, so these are the simple relation, but you have to think little bit more how to identify what will be the position. Here all all the things we have considered with respect to the load terminal. First, at the sending end, means at the sending end, what is the distance from the load? It is 100 meter. So at that time L is equals to 100 meter we have considered. Okay. Next, at the receiving end. At the receiving end means at this point. So that means the input impedance is same as your load impedance. So input impedance is same as load impedance, and potential at this length L is equals to 0. You have to identify. Okay. Next, 4 meter from the load. So 4 meter from the load means now the length you have to consider from the load side as 4 meter. Okay. So 4 meter from the load. So with the help of that 4 meter, you have to find out beta L, input impedance and potential. Okay. Similarly, 3 meter from the source means from load end how many meter? 97 meter. So the length will become as now 97 meter. Now when you are calculating this potential and input impedance, always you have to see from the load end what is the distance is covered. Okay. So this is the relation with respect to input impedance, with respect to the potential and with respect to the positions. We will take one more question. Okay, so one more question. A lossless line with characteristics impedance 75 ohm terminated with a load impedance 120 ohm, and the length of the line is given as 1.25 lambda. If the line is energized with a source is 100 volt RMS potential with internal impedance is 50 ohm. Determine input impedance and the magnitude of the load voltage. So these are the two things we have to calculate. One is input impedance, one is the load voltage. So how to proceed? First of all, so with the help of the given details, Z0 is equals to 75 ohm, load is given as 120 ohm, length of the line is 1.25 lambda, and source potential is 100 volt, and Zg is given as 50 ohm. Okay. Now here we have to calculate first beta L terms in order to determine the input impedance. Okay. Now what is beta? Beta is nothing but 2 pi by lambda, and length is about 1.25 lambda. Now this lambda will be cancelled out. 1.25 into 2, near about how much it will come? So it is 2 into 1.25 of pi tau. So you will get 0, this is for 5, so it is 2.5 pi, or I can write pi by 2 plus 360 degree. So that means one complete rotation plus 90 degree. Now this beta L tends to pi by 2. Okay. Now 10 beta L or 10 of pi by 2 is equals to infinite. So 10 beta L, if it is infinite, we have a relation for lossless line Z0 ZL J Z0 beta L divided by Z0 plus ZL 10 beta L. Okay. In place of this 10 beta L, you have to substitute infinite. So what you will do, take this 10 beta L as common outside. So we will get Z0 ZL divided by 10 beta L plus J Z0 divided by Z0 10 beta L plus J ZL. Okay. Now infinite, something by infinite is tends to 0. So this is tends to 0 and this is tends to 0. So we left with Z naught, J Z naught and J ZL. So this minus ZZ will be cancelled out and we will get Z naught square divided by ZL. So this is the input impedance Z naught square divided by ZL. What is Z naught? Z naught is 75 into 75. What is the load? Load is 120. After solving this, you will get 46.875 ohm. So this is my input impedance, 46.875 ohm. Okay, so this is the input impedance. Similarly, next we have to find out the magnitude of potential, load voltage. So V at Z is equals to 0, V naught we have to calculate, magnitude the load potential at this particular point. So at Z is equals to 0, V naught if I am calculating, what I will get? I will get Z in divided by Zin plus Zg into Vg. Done. So what is my Zin? It is 46.875 divided by 46.875 plus how much is Zg? Internal impedance is 50. And what is our source? Is 100. So if you solve this, you will get around 48.39 volt. So this is your V naught is equals to 48.39 volt. Okay. So this is your load potential. Now this is your V naught. Now once this V naught is known, next you have to calculate the load potential. So load potential VL, the formula is same as what is our VL? VL is equals to V naught e to the power j beta L minus j beta L. Now as we know that beta L is pi by 2, only the positive half we are going to identify, that is sine of cos of 90 degrees 0 and the sine of 90 degrees become 1. So here the VL will also have 48.39 volt. Okay. Only magnitude I am considering, not with angle. If I am considering angle, then angle minus 90 degree I have to substitute. Okay. So this is the basic relation for identifying the input impedance, input potential and the load potential. Okay. So depend upon these sort of questions you have to answer very neatly and step by step you need to follow, because each and every step will carry different sort of marks. Okay. So these sort of questions may come in your exams. These are the little bit complex one. So one more question we will take. Okay. So let us consider one more question, that is the incident voltage wave on a certain lossless line. So here we are discussing about the lossless line whose characteristics impedance is 50 ohm, phase velocity is 2 into 10 to the power 8 meter per second, and V plus Z of t means incident potential given in terms of time domain is 200 cos of omega t minus pi z volt. Okay. We have to determine angular frequency and the incident current in time domain. Few more questions are left. The section of this line for which z greater than 0 is replaced by ZL is equals to 50 plus J30 at Z is equals to 0. You have to determine the reflection coefficient, the reflection potential and the Vs at Z is equals to 2.2 means minus 2.2 is given because the load is present at Z is equals to 0. Your source is present at a distance of 2.2 means suppose this is my 2-wire line. Understand this, then it will be easy to represent. Okay, this is my load. Done. If this is my load, Z is equals to 0 I am considering because reflection coefficient is calculated at ZL. Now Z is equals to minus 2.2 meter means toward this direction where source is present. So Vs we have to identify. So Vs at how much distance? 2.2. So it is Z is equals to minus 2.2 because here we have considered load is present at Z is equals to 0. So the source will have in a negative distance or the distance is called as a 2.2 you can take. Okay, so here it is Z is equals to minus 2.2. So this is the source end. So this you can consider as a Vg. Okay, so this is the source end. So this is the thought process behind this particular question. You have to analyze it. Where my source will present, where my load is present, what are the conditions are given. According to that you have to proceed. So first I will calculate the angular frequency, but before that whatever the data is given I will note it down. Characteristics impedance is 50, phase velocity is 2 into 10 to the power 8 meter per second, incident potential V of Z comma t is 200 cos omega t minus pi z volt. So these are the given data. So omega we have to determine. Okay. So how to determine the omega? First we have beta value. From this equation you may remember that this is V naught cos omega t minus beta z volt. Minus z means positive direction, it is propagating total wave. Now here this is beta. What is the value of beta? Beta value is pi. So it is pi radian per meter. Pi rad per meter. Now we know that beta is equals to phase velocity is equals to omega by beta. This is my relation because beta is equals to omega root over of LC. Omega will be cancelled out. So here we have to determine omega. So phase velocity into beta. So omega phase velocity is how much? 2 into 10 to the power 8. And what is beta? Beta is pi. Pi means 3.14. So 2 is 8 to 6.28 into 10 to the power 8 meter per second. Sorry, radian per second. So this is my angular frequency. Over. Next we have to determine what is I plus Z comma t, incident current. As we know that incident current is equals to incident potential divided by the characteristics impedance. So here I can write V plus Z comma t divided by Z naught. So this is 200 cos of omega t minus pi z whole divided by Z naught. Z naught is how much? 50. So this you will get 4 cos omega t minus pi z. Done. This is in terms of ampere. So this is my current. Next, C. For C, the section of the line for which Z greater than 0 replaced by the load impedance at Z is equals to 0. At Z is equals to 0, ZL is equals to 50 plus J 30 ohm and Z naught is 50 ohm. Okay. So what is the reflection coefficient? Simple. So reflection coefficient is ZL minus Z naught, ZL plus Z naught. So ZL is 50 plus J30 minus 50 divided by 50 plus J30 plus 50. So numerator is J30, it is 100 plus J30. So if you solve this, your reflection coefficient will be around 0.287 angle 1.28 degree. So this is your reflection coefficient. Okay. This is your calculation for angular frequency omega. This is your incident current. This is your reflection coefficient. Next we have to identify what is Vs reflected coefficient at the source, Vs minus, and Vs at Z is equals to 2.2. So let me erase it. Okay. So you have to calculate Vs minus of Z. But the reflection coefficient, we know Vs minus of Z divided by Vs plus of Z. Done. And that to e to the power j beta Z is also there, because beta is there means we have to consider it. So this is only the magnitude part I am taking. So Vs minus of Z reflection coefficient, Vs plus of Z e to the power j 2 beta Z. Okay. Here I can write Vs of minus Z reflection coefficient, Vs of plus e to the power j 2 beta Z. So now we have to calculate all these factors. Okay. Now reflection coefficient we have identified how much? 0.287. 0.287. Only the magnitude I am considering. Okay. Vs plus Z magnitude is how much? 200. Okay. And that too e to the power j pi Z into j 2 beta Z, because Vs of Z comma t, V plus what it is written in terms of incident. So this is in terms of what? This is in terms of instantaneous factor, omega t minus pi Z. You have to represent this one in phasor form, means you have to remove this omega t. So Vs plus of Z, this I can write 20 e to the power j pi Z. Okay, j pi Z. So this factor I have multiplied here, and this Vs of Z I have substituted. So it is 0.287 into 200 and e to the power j, this is pi Z plus 2 beta Z. Okay. So this 2 beta Z you can write 1.28. So resultant will be 57.5 e to the power j pi Z, and this one is 1.28 beta Z. Okay. So 2 beta Z you can identify as 1.28, and this is my reflection potential, 5 j pi Z 1.28. Okay. And this Z is take outside, because here beta value is near about pi. So pi into 2, it will 1.28 and 2 will be multiplied. So you will get around Z component. Okay. Beta is pi 3.14. 2 into 3.14, 826, one correction. This is 6.28 and this is 6.28. Done. So this will be my potential value. So this is my reflection potential. Now we have to calculate what is Vs at 2.2. Now Vs plus e to the power minus j beta z plus Vs minus e to the power j beta z. Done. This value we know, this value we have calculated now. Where we have to calculate? At z is equals to minus 2.2. So in place of z, you have to substitute minus 2.2. Vs plus we have identified, Vs minus also we have identified. This is Vs plus, okay, this is Vs plus, substitute this value here. This is Vs minus, substitute this value here. In place of e to the power minus beta z, in place of z, you have to substitute z is equals to minus 2.2 and you have to solve it. After solving this, you will get a complex term because these are all complex in nature. So potential you will get around 200, let me write, 200 e to the power j 2.2 pi plus 57.5 e to the power minus j 2.2 pi minus 6.28, which is equals to 257 angle 36 degree. So this is your Vs. So like this you have to calculate the incident potential. If it is given, you have to calculate the reflection potential. Then what is the source relation as per the general solution you have to take, and in place of the unknown quantity substitute the values. So like this you have to proceed. So these are the questions, little bit tricky questions. You need to think of it and you have to answer it. Okay. So next class we will discuss on the rest part of a transmission line, that is called Smith chart. So first of all I will discuss with respect to theory, and then we will discuss with respect to the Smith chart, how we can solve this sort of questions using the Smith chart, how it is easy to calculate. Here all theoretical calculation we are doing, but with the help of Smith chart we can calculate all these parameters in very minimum effort with the help of that chart. Okay. So next class I am going to discuss about the Smith chart. Thank you all.